Let me take you to a place where time simply stops. Not metaphorically, not poetically, literally. Imagine falling toward a black hole, one of the most extreme objects in the universe. A place so dense, so powerful, that nothing, not even light, can escape its pull. But something even stranger happens as you get closer. Time begins to slow down. To you, the fall feels normal. Seconds tick by. Your heart beats. But to someone watching from far away, your movement slows and slows until it looks like you're barely moving at all. Eventually, you appear completely frozen, stuck at the edge of the black hole, unmoving forever. This isn't science fiction. This is Einstein's theory of general relativity, tested and verified. In our daily lives, time feels constant. Clocks tick, seconds pass, and we age predictably. But Einstein revealed something stunning. Time is not absolute. It's part of a flexible fabric called space-time, and that fabric can be stretched, compressed, and twisted by gravity. The stronger the gravitational field, the more space-time is warped. And that means the slower time flows. This phenomenon, called gravitational time dilation, has been proven experimentally. On Earth, astronauts aboard the International Space Station age just a bit slower than people on the surface. Even your head experiences slightly more time than your feet, because gravity is weaker a meter higher. Now scale that up. Near a black hole, gravity becomes unimaginably strong. And at the event horizon, the point of no return, it becomes effectively infinite. From the outside, time at the event horizon appears to come to a standstill. To distant observers, you never cross the event horizon. You just freeze, a living snapshot trapped on the edge of eternity. But here's the paradox. From your perspective, nothing is wrong. You feel no resistance, no pause. You fall straight through the event horizon in seconds. Time keeps ticking for you. But the rest of the universe sees you locked in place, paused forever. This contradiction, where time both moves and doesn't, is one of the strangest consequences of general relativity. Black holes don't just trap matter, they fracture time itself. Imagine what this means across the universe. Every black hole, and there are billions, could be a cosmic time vault. At their edges, entire stars, planets, and even alien civilizations might be captured in their final moments. From our perspective, they never finished falling. Their light just grows dimmer and slower, a ghost of what once was, still hanging on the edge of time. It's possible that right now, some of the first stars ever born are still visible, not because they exist, but because they're frozen at the edge of black holes. But can time do more than pause? That leads us to one of physics' biggest mysteries, the arrow of time. Why do we remember the past, but not the future? Why does time flow one way? The best explanation we have is entropy, the tendency of systems to move from order to disorder. It gives time its direction. But entropy is deeply tied to thermodynamics, and in a black hole, the rules break down. What if entropy collapses inside a black hole? What if time doesn't just pause, but loses its direction? Could time reverse? Could it move in a loop? Or fracture into branches? Some physicists have speculated that black holes might contain entire universes, pocket realities where time starts over. Others wonder if time inside a black hole moves sideways in a way we can't perceive. And then there's dark energy, the mysterious force accelerating the universe's expansion. Some theories suggest that black holes might leak time or energy into the fabric of the cosmos. That distortion could subtly influence the expansion of space, or even tie into the structure of spacetime itself. Now add quantum physics to the mix. In the quantum world, particles can exist in multiple states at once, a superposition, until they're observed. But what happens when a quantum particle falls into a black hole? Do the probabilities collapse? Is the information lost? Or, as Stephen Hawking once proposed, does it simply vanish? This is the infamous black hole information paradox. If information is destroyed inside a black hole, it breaks a fundamental rule of physics, the conservation of information. Quantum mechanics says information must be preserved, always. But black holes seem to swallow it permanently. So where does it go? One theory is that all the information is stored at the event horizon, encoded on the surface like a cosmic hologram. A 3D reality imprinted on a 2D shell. This leads to the holographic principle, an idea so radical it suggests our entire universe might be a projection, a hologram of information encoded at its edges. And if that's true, then black holes are databanks of frozen time, holding every particle, every thought, every photon that ever crossed their boundary. Maybe black holes don't destroy information. They just pause it, like a computer buffering a video. The information is there, waiting to be rendered. Now picture this, time not as a flowing river, but a landscape, full of hills, valleys, cracks, and loops. In this landscape, black holes are the deep ravines, where time sinks, stretches, and eventually folds into itself. Could we navigate that terrain? Could we one day use black holes as gateways to other regions of spacetime? Could we dive into a black hole, encode our information, and emerge somewhere else, or someone else? Some scientists take this even further. They wonder if black holes are connected through wormholes, hypothetical tunnels linking distant points in space and time. If real, they could allow faster-than-light travel, or even time travel itself. But there's a cost. Approaching a black hole is a one-way journey. Tidal forces near the singularity grow so extreme they'd tear matter apart, atom by atom. The very fabric of you would be unraveled. And yet, some theories suggest that if you could survive the fall, you might pass into a white hole, the theoretical opposite of a black hole, where all the information comes flooding out again. So maybe, just maybe, what falls in does come out somewhere else. We're only beginning to understand these possibilities. The physics is still incomplete. Quantum mechanics and general relativity don't fully agree. But we're getting closer. Every time we observe black holes, like with the Event Horizon Telescope, which captured the shadow of a real one in 2019, we glimpse the boundary between reality and something more. Something deeper, stranger, timeless. So the next time you look up at the stars, remember, somewhere out there, a moment is still falling and never arriving. It's frozen, waiting, preserved in the silence of curved spacetime. Forever. That's the narration. Provide Take 60 prompts for this in the same manner I have asked for.